Good afternoon, students. We are actually discussing Unit 5. Already last week we discussed kinematics. You know, kinematics means study of the body in motion without considering forces. We know any body want move, we need force. But excluding force, we are studying about other. What other? What is the how much acceleration taken place? What is the velocity? How much distance covered? How much time taken? So kinematic means study about relationship between distance or displacement, velocity, acceleration, and time. Okay, we did many problems, and we started about kinetics. What is kinetics? Study of the body in motion with considering all forces. Or other definition, study of the body, the study about relationship between force, mass, and acceleration. If you say acceleration, it includes all displacement, velocity, acceleration. Everything is included. So kinetics means study of the body in motion condition with considering all forces. Okay. We know Newton's second law of motion, F equal to ma. F equal to ma. Then remember all the equations, the three equations of uniform accelerated motion. V equal to U plus AT. S equal to UT plus half AT squared. Then V square equal to U square plus 2AS. So this problem already we discussed. Okay. For your remaining, I'm explaining again here. Your body has 50 kg mass. Find its weight. They're asking weight on Earth. See, you know, at a different planet having different gravity, acceleration gravity, no. So on the Earth they given G 9.81. On the Moon they given G equal to 1.7 meter per second square. On the Sun, the G gravity value 270 meter per second square. They asked weight. We know weight equal to what? Mass into gravity, M into G. So they applied M into G at Earth. 50 into 9.81. Therefore, the weight equal to 490 Newton on the Earth. See, on the same body, the 50 kg body, if it is in Moon, the weight is 50 into 1.7, therefore 85 Newton. Just imagine. Because due to the gravity, if you change the gravity, the weight also changes. Then weight of the body on the Sun. You know, weight equal to mass into gravity. Here they mention force. Okay, mass into gravity, M into G, 50 into 270. 13,500 Newton. Just imagine. The same body, if it is in Sun, the weight is 13,500 Newton. Now come to here. A body of mass 7.5 kg is moving with the velocity. Students, moving with velocity, that is called initial velocity. There is two velocity. Initial velocity, final velocity. Okay. So the force inward, if the force 50 Newton, determine velocity after 2 seconds. Students, remember whether this problem belongs to kinematics or kinetics. You have to differentiate first. How do you differentiate kinetics and kinematics? Without a force, we are studying the motion of the body is called kinematics. With the force, see in this problem the force is here. So your mind goes to this problem belongs to kinetics. With the force of 50 Newton is applied on the body, determine velocity after 2 seconds. So after 2 seconds means what velocity? Final velocity. So given data, mass of the body is 7.5 kg. That initial velocity, no, you have to write always symbol, students. Moving with means initial velocity, U equal to 1.2 meter per second. Force equal to 15 Newton. And time t equal to 2 seconds. They asked the final velocity, V equal to question mark. Okay, we know V equal to U plus AT. We want the VU. u plus at. We know equation. So you have to always remember three equations, students. V equal to u plus at. S equal to ut plus half at square. V squared equal to u squared plus 2as. Okay. So in this question, they are given initial velocity and time also given. So what we need acceleration. How do you calculate acceleration? We know Newton's second law. We know Newton's second law. What is the Newton's second law? F equal to ma. Students, F equal to ma. Therefore, a equal to F divided by m. What is F value? 15. What is m value? 7.5. What is acceleration? 2 meter per second square. So we want final velocity. No, v equal to u plus at. Therefore, u equal to 1.2 plus acceleration just now we calculated. 2. What is the time t? 2 seconds. V equal to 5.2 meter per second is final velocity. Understand? Then this problem also we will discuss last class. Okay. This also we discuss. Lot of problem we discussed. So why am I repeating this one? Just remember this we are discussing kinetics of particles. How do you identify kinetics of particle? The force involved in the equations in the problems. So we are used to only Newton's law of motion. Students, we have used the Newton law of motion, second law of motion. That is Fa equal to ma we used. Then other three equations used. V equal to u plus at, S equal to ut plus half at square, V squared equal to u square plus 3s. Understand? So we have used the four equations. We calculated based on the given data. We calculated other things. Okay. So today what we are going to discuss? D'Alembert principle. D'Alembert principle. Very important. Two more questions. Class rep, can you read the statement? D'Alembert principle.
Yes, sir. D'Alembert's principle. If a rigid body is acted upon by a system of forces, this system may be reduced to a single resultant force whose magnitude, direction, and the line of action may be found out by the methods of graphic statics.
Again repeat.
Okay, so if a rigid body is acted upon by a system of forces, this system may be reduced to a single resultant force whose magnitude, direction, and the line of action may be found out by the methods of graphic statics.
See, we know what is second law? F equal to ma. Students, we know F equal to ma. If I am writing F minus ma, that is called a D'Alembert principle. If I am writing F minus ma, this equation is called a D'Alembert principle. Understand? What is the D'Alembert principle? See, I told you know there is two types of equilibrium. Students, I told you the very first chapter. I told you two types of equilibrium: static equilibrium, dynamic equilibrium. Just remember, static equilibrium, dynamic equilibrium. What is the difference? See, very simple example I am telling now. Just imagine the fan is not switched on. What is the condition of fan? Just hanging. Just hanging, or we already tied at the end at the floor, at the roof. Static condition. That is static equilibrium. What is equilibrium? The body is in rest condition. Even though we force applied, the body must be stable, not moving. This is static equilibrium. The fan is now static when switched off. Now we are switched on. What will happen? The fan is rotating. We are changing speed, no? Speed 1 to 0 to 1, 1 to 2. The fan also rotating, but not non-uniform motion, non-uniform rotation, ununiform rotation. Understand? It is rotation. And with respect to the perpendicular axis, vertical axis, it's a uniform rotation. Understand? It's not moving zigzag that side, this side, no. So that is called a dynamic equilibrium. Students, understand? Dynamic equilibrium. You can apply anything for dynamic equilibrium. Just imagine the aeroplane is moving. Stable condition. Just imagine slowly flying. Or just imagine the car, your college bus or your bike. You are moving on a straight line road, 60 kilometers per hour. You are moving on the straight line. That is called a dynamic equilibrium. When you can say non-dynamic equilibrium, suppose see the road, some fellow know that moving that direction, zig zag, that direction, no, unnecessary making noise. That is also very danger, no. The people going sideways, they are very worrying. Why did people going that no? So dynamic equilibrium means that is mathematically we can write. That is a mathematically we can write F minus ma. F equal to ma means motion, body in moving condition. F minus ma means dynamic equilibrium. Even though it's moving, it's a dynamic balanced equilibrium. See, if you that's why we are telling, if you are having balanced mind, we can achieve anything. Stable mind. We are telling, that fellow is not stable mind, frequently changing. The stable means the thinking, the thought process is slowly, uniformly. Similarly, the motion. The motion also, see, just an example I given, the fan. Fan now rotating. Is equilibrium, no? What equilibrium? Dynamic equilibrium. So mathematically, you can say F minus ma. That is called D'Alembert principle. Students, what is D'Alembert principle? You can write a statement, but mathematically, the P minus ma. P means also force. Students, P also force. I'm telling F minus ma equal to 0. Okay, that is a statement. It states if a rigid body is acted upon by a system of forces, the system may be reduced to a single resultant force whose magnitude, direction, and the line of action may be found out by the methods of graphic statics. Okay. Or other thing, you can simply write this F minus ma equal to 0. That is enough. What is F? Force. What is M? Mass of the body. What is A? Acceleration of the body. Understand? The minus ma, no, the minus ma, the minus ma means inertia force, reversed effective inertia force. Students, the minus ma means reversed effective inertia force. Understand what is the principle? You can write statement, or other simply you can say F equal to ma. F equal to ma means Newton's second law. F minus ma equal to D'Alembert principle. F minus ma equal to 0. F minus ma equal to 0. Dynamic equilibrium. Okay. Now I am sharing small that online video. You can see that what is D'Alembert principle. Okay.
A very important topic on dynamics, that is kinetics of a particle. This is also known as particle dynamics. Now, this essentially is based on three important principles. Starting off with the elements principle, then we have the work energy principle, and then finally we're going to go through the impulse momentum theory. Okay, now in this part one of this video series, I'm going to talk about the element principle, which is absolutely based on the Newton's second law of motion. When you talk about the work energy principle, this in fact is completely based on the difference of kinetic energy. It states that the kinetic energy at position 1 minus the kinetic energy at position 2 is equivalent to the work done, okay, or the difference in kinetic energy at two different points, two different positions is equivalent to the work done. And then finally, in the third video of this lecture series, we'll actually go through this impulse momentum theory. Okay, and this actually talks about the law of conservation of momentum. Right. So in this lecture, let's talk about this fellow, John Durand Lambert. Okay. Now, in order to clearly understand what this theory has to say, we need to go through Newton's second law of motion. Newton's second law of motion. Well, I'm pretty much sure that you guys must have gone through Newton's second law of motion in 9th grade, 10th grade, or in 11th grade, right? But I'll briefly explain to you what it is. Okay, so let's say we have a body. Let's say this body is having a mass m, and this body in fact is acted upon by a bunch of forces. Let's call this force as F1, this is F2, and this as F3. Now, the effect of all these forces is going to be like this. All of this is going to have one single resultant, something of this sort. Okay, let's just assume for convenience and for simplicity that the overall effect of these forces is having a resultant of magnitude r, and which is going to induce the body to move somewhere along in the horizontal direction. Let's say in the x direction. Right? So what Newton's second law of motion says is the summation of all the forces, all these forces acting on a body is equal to the product of mass, this m, multiplied by the acceleration. So this is essentially a mathematical expression of the second law of motion. Now, what we'll do right now is that we'll try to apply the Newton's second law of motion, and we'll try to calculate either the force or the acceleration. Let me try to explain you what exactly I'm trying to say. So here we go. Let me remove all of this, and let's just say that upon this frictionless surface, this is ground, in fact you can say this is frictionless shortcut. Okay, let's say we have a body having a mass. Let's just assume this mass as 10 kgs, and let's just say that this is being acted upon by two forces from two different directions. Now let's say this force is having a magnitude of 100 newtons, and one more force is there, okay, acting from the right to the left of your screen, something of this sort, and this in fact is having a magnitude of let's just assume it as 50 newtons. Okay, so how can Newton's laws of motion or the second law of motion help us in calculating the acceleration that this body is going to have, or this object is going to have? Acceleration. Okay, let's say that the acceleration is represented by small e. Okay, so what Newton's law says is this: summation of all the forces is equivalent to, let's say, in the x direction. Right now we are working in the x direction, this way. This is the y-axis, and none of the forces are acting in the y direction, so analysis along this axis is not to be done. Analysis along the x-axis is to be carried out right now. Summation of all the forces in x direction is equivalent to the product of mass and acceleration. So what are the forces acting? 100 and 50. 100 is towards the right, taken as positive, and if there is a force acting over here, it has to be taken as negative. So we have this 100 positive, we have this 50 negative, and all of this is going to be equal to the product of mass. How much is the mass? It's 10 kgs. So let me write this as 10 multiplied by acceleration. So guys, you essentially need to solve this equation, right? And then you're going to immediately get the value of acceleration. This is 100 minus 50 is 50. 50 over 10 is obviously 5. So the value works out as 5 meter per second square. So this is the acceleration that this object or this body or this system is going to acquire when these two forces are acting simultaneously. That is 5 meters per second square. Okay, let me give you one more intuition in this concept of acceleration. What we basically calculated is this acceleration as 5 meter per second square. So you can essentially say, or you can essentially write this as 5 meter per second per second. What does this mean? This means in a span of 1 second, the body will acquire a velocity of 5 meters per second, or will increase, the velocity of the body will increase by an amount of 5 meters per second. So initially, the velocity is going to be 0, but let's say at t is equal to 1 second, the velocity is going to be 5 meters per second, right? And let's say at t is equal to 2. So previously it is 5 more. So the velocity at t is equal to 2 seconds is going to be equal to 10 meters per second. So this is why acceleration is so helpful in computing the velocities at different time spans, right? And this actually is a sort of an equation of motion, which is this one. Final velocity is equal to initial velocity plus acceleration multiplied by time. Okay, so if the initial velocity is 0 and you take this t is equal to 1, you have the acceleration over here in the form of 5 into 1 is how much? It's going to be equal to 5 itself. So velocity final is 5. Right. So guys, that was all about computing acceleration by applying the Newton's second law of motion. Okay, let me rub all of this. I'm pretty much sure that up till now you must have got a good idea as to what this Newton's second law of motion has to say and how this can be applied to calculate the value of acceleration. Now, let's take one more example. And here we are not going to calculate the acceleration. We will be given the acceleration and we'll try to find the force by which that sort of acceleration can be produced. Let me try to draw this and we can understand this in a better way. Let's say we have a body. Okay, so this body over here is having a mass again 10 kgs. Let's say we want to apply a force whose magnitude is unknown. Let's just assume that this force now is represented by P. Okay, now due to this force P, this body is having an acceleration of, let's just assume this has 5 meters per second square. So what we are supposed to do is we have to calculate this force P, because of which this 10 kg block is accelerated by an amount of 5 meters per second. So this is going to be very simple. So you have to just apply the Newton's second law of motion. It goes like this: summation of all the forces, and here the forces acting are along the x direction. So we have to take this subscript is equal to mass into acceleration. Force obviously is P. Okay, and again assuming this has frictionless, right? There is no friction. Kinetic friction is equal to mass is how much? This is 10 multiplied by what? It's the acceleration. That's 5. So in this way, you can actually compute the value of force which needs to be applied, that is P, which is going to work out as 50 newtons, in order to produce an acceleration of 5 meters per second. Right. So that was all about the application of Newton's second law of motion. So guys, let's take this session forward and let's try to understand what this fellow Sean Deron Lambert has to say. Okay, for understanding his principle, what we'll do is we'll again consider a frictionless surface, and let's say above this frictionless surface we have a body having a mass m. Okay, now this mass m is being acted upon by a bunch of forces again, say in the form of F1 and F2, and let's take this F3 also. Now, all the three forces can be written by one single force in the form of resultant. Let's say that the resultant, for simplicity, be acting somewhere along in the horizontal sense, because of which there is going to be some motion along this direction. Okay, and the collective effect of these forces can be written in the form of mass into acceleration. What we'll try to do is we're going to enclose this in a system like this. Okay, and let me tell you what D.L. Lambert has to say. D.L. Lambert says that if this entire thing is assumed as one single system, and since this is in motion, and in order to bring the system into equilibrium, what we need to do is we need to apply a force of same magnitude, that is mass into acceleration, but in the opposite direction of motion. So this is the direction of motion, and this force is actually acting in the opposite direction of motion, and this force is what he terms as the inertial force. Inertial force. So guys, according to D.L. Lambert, this is what he says: summation of all the forces, okay, acting on the system, acting on the body, acting on the object, minus the inertial force, right? This is F inertial is equal to 0. So in order to bring this system which is in motion, right, we need to apply a force of equal magnitude, mass into acceleration, but in the opposite direction. And this equilibrium, he terms it as the dynamic equilibrium. Dynamic equilibrium. Okay, now you guys must have heard about static equilibrium. Let's take this duster for example. Okay, what is the state this duster is in right now? It's in static equilibrium, right? All the forces, the atmospheric, due to the atmospheric pressure, there are forces acting from this side, from this side, from this side, and this side, and there is going to be a reaction offered from my hand to the palm of my hand over here, right? But does this duster move? No, it does not. Okay? So this duster can be assumed to be in a state of static equilibrium. But as far as this moving object is concerned, this is right now in a state of dynamic equilibrium. This is sort of a figment of imagination. Okay. Anyways, if we were to frame the statement of D'Alembert, it would be something like this: a system of forces acting on a body in motion is in dynamic equilibrium with the inertial force. So that was the statement of D'Alembert. Now let's take up one more example. And with the help of this example, I'll try to help you to frame the equation with the help of Newton's second law of motion and also with the help of D'Alembert. Okay, so here we go. Let me rub all of this. And this example that we're going to take right now is going to be absolutely based on an inclined plane. So let's say we have an inclined plane over here, something like this. And onto this plane, we're going to have a body, an object, something of this sort, having a weight W. Okay. Now let's say that the inclined plane is at an angle of theta, right? So I'm going to be doing two different stuffs. Over here, I'm going to be applying the Newton's second law of motion, and over here, you're going to see that we are going to be framing the equation with the help of D'Alembert's principle. Let's go ahead and do this. So since this block is in contact with this inclined plane over here, and let's just assume that this over here is having a friction, let's say mu k, right? Weight is obviously going to act downwards, so it's going to be something like this. This is going to be W, and this way, this W is going to have two components like this. This is what we call W cosine theta. Now, obviously, this is going to be theta. This is going to be W cosine theta. And over here, this component is what you refer to as W sine of theta. So this is actually, for our convenience, the axis that we're going to be taking. This is the x-axis, and this over here is the y-axis, right? And let's just say this is the positive x-axis, right? Since motion is going to happen somewhere along this direction. We'll try to frame the equation from both these philosophies. Okay, since the object is in contact with this plane, so this plane is going to offer some sort of normal reaction, absolutely perpendicular to this plane. We're going to have a normal reaction. Let's just say this normal reaction is given by n, right? Now, since there is some kind of friction that this surface is offering to this block, there is going to be a friction force also. Now, obviously, because of gravity, this block will have a tendency to go downwards, because of which there is going to be a friction force acting along this direction. Let me go ahead and make this friction force will be along this direction. Its magnitude is going to be mu n. So since we are dealing with moving bodies, we have to use this kinetic friction, mu k n, right? So first of all, let us try to frame the equations with the help of Newton's second law. Now, Newton's second law is this: summation of all the forces is equal to mass multiplied by acceleration. So there are essentially two different modes in which the forces have been lined up. One along the plane, while the other perpendicular to the plane, x, and that's going to be y. Okay, so let me take this into consideration. X. Summation of all the forces in x direction is going to be equal to mass into acceleration, because it's going to move. Okay, it's x-axis, mass into acceleration. As far as the y-axis is concerned, there is no motion, and here the summation of forces is going to be equal to 0. Okay, so W sine theta, since this direction is positive, so we have this W sine theta. Okay, what else? So we've got this mu k n. So we have used this. Let me circle this. I'm going to write this as minus mu k n. Anything else? So I've used this also, right? So these are the two forces acting along this direction, and both of them will be equal to mass into acceleration. There is something else that you can do this: summation of all the forces in y direction is equal to 0. Why? Because there is no movement. If there is no movement, there is no motion, then there is not going to be any acceleration. That means acceleration is 0. So if acceleration is 0, m into 0 is 0. So summation of all the forces will be 0. So we have this. Let's take this as positive. If we have this, let's take this as negative. So n minus w cosine theta, n minus w cosine theta is equal to 0. Okay, so this is exactly how equations can be framed with the help of Newton's second law of motion. This is going to be your equation 2, 1, and this is going to be your equation 2. Now let's do the same stuff with the help of this guy. D'Alembert's principle. Let me write this completely. Okay, so what D'Alembert is trying to say is this. Okay, he modifies the Newton's second law of motion. So as far as English grammar is concerned, you must have heard about active and passive voice. So if you consider Newton's second law of motion as the active voice, then this over here, summation of all the forces minus ma is equal to 0 is going to be the passive voice, in which this over here is the inertial force and this over here is the system of forces acting on the object, on the body, okay, whatever you may call it. Anyways, so let's try to do this analysis, okay, somewhere along the x-axis. Along the x-axis, motion analysis, right? So we have this w sine theta. Okay, let's write this w sine theta. Anything else? We have this mu kn. Again, this is opposite, minus mu kn. And if we apply an inertial force minus of mass into acceleration, then all of this entire stuff will be in dynamic equilibrium. That's it. So what D'Alembert has done is written a passive form of this equation, right? And this stuff is going to be exactly the same. You don't need to worry much about this. Summation of all the forces in y direction is equal to 0. You've got this reaction force n upwards and this w cosine theta downwards. So n minus w cosine theta is equal to 0. So these are the two equations, and a bunch of outputs can be calculated. So guys, in this lecture, we've seen the Newton's second law of motion and how it is deeply connected with the D'Alembert's principle. Again, I would like to explain this, summarize this. Newton's second law of motion's mathematical formulation is this: summation of all the forces is equivalent to the mass into acceleration. And if you bring this mass and acceleration, product of mass acceleration over here, something of this sort, this automatically can be referred to as the inertial force, which when applied in the opposite direction of motion will bring the entire system in the state of dynamic equilibrium. And that's exactly what John D'Alembert has tried to explain in his theory. So guys, that was all from my side for today. If you've got any doubt or query,